Yeah, thank you very much. First of all, thank you very much for having me here today. So I'm going to talk about the GRAMS project. So GRAMS stands for Gamma Ray and Antimatter Survey. And it's a newly proposed project, and we already formed an international collaboration. And it will be the first balloon experiment using a low-cost, large-scale liquid argon time projection chamber detector. And the project can be expandable to a satellite mission. And also GRAMS will be the first experiment to target both MeV gamma ray observations and also antimatter-based indirect dark matter search. So first paper was published in Astrophysical Physics last year, and we also submitted SNOWMAS LOI. So let me start with the gamma ray observations. So this is the current status of X-ray and gamma ray missions. As you can see here, MeV region is poorly explored, so-called MeV gap. And in this energy band, Compton scattering process dominates. And in order to reconstruct event, you need good energy and spatial resolution. So which make it difficult to have a large-scale detector. So what we can do with MeV science, this is just an example. We may know the high energy gamma ray region from Fermi and X-ray region from Newstar or Chandler, but we don't know the spectrum in between. So it looks like maybe we may see some transition, slope changes here, so indicating that we may be able to study some transition physics processes. And also nuclear lines are usually in this energy band, so we can study nuclear synthesis of astrophysical phenomena, including the supernova explosions. Also, multi-messenger astronomy is very popular these days, and MeV gamma rays could be electromagnetic counterparts of gravitational waves from neutron star merger or merger remnants. And also we can do dark matter search with MeV gamma rays. MeV gamma rays could be emitted from dark matter annihilation or decay, or evaporating primordial black holes that could be part or all of dark matter. So let me talk about GRAMS detector. And our detector has a LArTPC surrounded by plastic scintillators. For antimatter survey, time of flight, plastic scintillators work as time of flight to measure velocity of incoming particles. And LARTPC works as a particle tracker or calorimeter. And for gamma ray observations, plastic scintillators work as beetle counters to reject charged particles. And LARTPC works as a Compton camera or calorimeter. So this is just an example. When charged particle comes in, ionize and excite argon atoms, the scintillation light will be measured by silicon PMs, and ionized electrons will be drifted to the anode plane due to the E field inside the LARTPC. And XY position can be obtained based on the position of anode wires or pads, and drift time provides Z position, which allows us to have 3D tracking image. So this is the example for the Compton scattering. So based on the position and energy, we could get the cone angle theta. So I would say large-scale low-energy threshold LARTPC has been well studied and widely used in dark matter neutrino underground experiments. And our plan is to bring it to the space for balloon and satellite mission. Also, our unique, maybe fresh idea is to segment LARTPC into cells so that we can localize and minimize the coincident background events. This is very important because we can have a lot of background events, unlike underground experience. So let me talk about a little bit more why we chose LARTPC. So it's very cost effective because argon is most abundant gases on Earth compared to the high purity crystals. Also, like I said before, Z position will be obtained based on the drift time. So we don't need to form a multi-layer design. In the multi-layer design, we need electronics each layer, meaning that if you have 10 layers, you need 10 times more readout electronics for the same volume of detector, which may limit the size of the science payload. So additionally, so semiconductor detector usually mounted on the mounting frame and preamp should be nearby, which creates a lot of dead volume, but for LARTPC, almost no dead volume inside. And also, additionally, we're gonna have we are capable of discriminating electronical events from nuclear events based on the pulse shape, as successfully demonstrated in the direct atmospheric experiments. This means we can reject neutron events, so that will be the main background event for MeV gamma ray observations. So again, LArTPC is cost effective, so we can easily expand to a large scale, and also almost no dead volume, so we can expect to have a high detection efficiency. So this is expected sensitivity to MeV gamma rays. So red line is a single balloon flight, and we can expect to have an order of magnitude improved sensitivity compared to the previous experiments. And blue line is a satellite mission, which will be comparable to the future mission like eAstrogram or MeV. And we are currently evaluating sensitivity to MeV gamma rays from dark matter annihilation decay, and also evaporating primordial black holes. This is just an example discussed in the previous session. So eAstrogram could explore a new parameter space here, and GRAMS could be comparable to eAstrogram. Also, GRAMS may be able to explore a new parameter space for PBH, so stay tuned. Moving to the antimatter survey. So as discussed also in the previous sessions, AMS and Fermi reported very interesting results indicating a possible detection of dark matter signal. So Fermi reported some gamma ray excess from the galactic center region. This could be explained by dark matter, 50 GeV dark matter decaying to dB bar, or some astrophysical objects like millisecond pulsars. Also, AMS result indicated there is small excess here in the antiproton flux. This looks small, but according to this paper, it's a 4 sigma excess. And this could also be explained by 50 GeV dark matter. And again, this region is excluded by film dwarf galaxy observations. But as discussed previous session, also this limit is relaxed with upgraded J factor calculation. But still, there is a strong tension here. And also, AMS reported the anti-helium-like event detection. So all these signatures are very skeptical. So it's very difficult to conclude they're from dark matter, because there are many astrophysical objects that could mimic the signal and some uncertainty in the model. So we really need a new approach and new experiment to identify these signals. So GAPS and GRAMS are targeting low energy antideutron, because it's essentially background-free dark matter search. So green line is the primary antideutron flux from dark matter annihilation decay, and red line is the secondary antideutron flux from cosmic ray interaction. In this case, antideutrons produced in the shower, so peak has a higher energy. So if you look at low energy region, signal to background ratio is huge. This is the reason we call background-free dark matter search. So these are the sensitivity for GAPS and GRAMS, and the current upper limit from BESS. So GAPS is a current generation experiment that we are scheduled for the first science flight from Antarctic in 2020. And Yamatani-san will have the poster session about GAPS. And GRAMS is the next generation mission. So let me talk about the detection concept. So when antideutron
2 minutes left, please.
Sorry, to me? Sorry.
2 minutes. Please.
Okay. Yeah. When antideutron comes into the instrument, it stops inside, forming an exotic atom, meaning that antideutron is bounded by argon nucleus. And here, it's excited state and emitting atomic X-rays while in the de-excitation. And at the end, nuclear annihilation takes place. So based on these atomic X-rays annihilation products, we can identify incoming antiparticles. So LArTPC has almost no dead volume, so we can have an excellent 3D particle tracking capability and high particle detection efficiency, which may allow us to have extensive antideutron sensitivity. So this is the same plot as before. And GAPS will start investigating this region, and GRAMS will be able to fully cover this region. So let me talk about the timeline. So we are in the R&D phase to validate detection concept and developing the event reconstruction techniques. With Waseda University Hancock Group support, we are evaluating their calibration data with gamma ray source. We are expecting to have a first science flight in 5 to 10 years, and maybe science satellite flight in 10 plus years. this is our collaboration. It's a small group, but we are still expanding. So my group at SWAC, we moved to Northeastern University, and we have some technical support from Waseda University and some theoretical support. So we had a second collaboration meeting this summer. And again, we are expanding our collaboration, so please join us. Yeah, thank you for your attention.